In this video, I want to talk about how we can use System Verilog to define finite state machines. So if you remember from before, any finite state machine was containing three main blocks. So this one you can see an example of a more FSM in which the output is only dependent on the current state of the system. But nonetheless, we had a next state logic unit, a set of flip-flops, and an output logic unit. So when we want to design FSM, we basically break down our design into three different sections, each one implementing one part of the circuit. So let's just go over a very basic example. This is a circuit called divide by 3. So basically when you reset the system, you start at state 0 and your output, which is Q, is 0. Then on the next edge of the clock you go to a state 1. Here the output is 1. On the next edge of the clock you go to a state 1 and your output is 0. And on the next edge of the clock again you change your state, you go to a state 2 and your output is 0. And then on the next edge of the clock you go to a state 0 again and your output is 1. So as you can see on the basically on reset or 0 edge of the clock your output is 1, then for 1 and 2 it is going to be 0, and then for 3 again it's going to be 1. And then if you continue this for all the product of three integer product of 3, your output is going to be 1, while for the other numbers your output is 0. So that's why it's called a divide by 3 circuit. Let's just say we want to implement this circuit using System Verilog. So the module that we want to create looks something like this. So there are some known keywords that we see everywhere. When we have a module, we definitely have a module and end module for the System Verilog. Then we have the name of the circuit or module. Here it's called divide by 3 FSM. For the inputs we have a clock, a reset, and a Q output. So this system, as you can see here, doesn't have any other sets of inputs or outputs. Only reset and then one output Q, and then since it's a finite state machine it requires to have a clock signal as well. So these are the three components that we have for the system. So this one is the flip-flop or the register part. This one is the next state logic unit, so basically the combinational logic circuit that calculates our next state, and this one is the output logic unit. But if you remember from before, when we were using and designing finite state machines, first we came up with some abstract names for the states, and then we had to do encoding to basically interpret those states as binary numbers. So this is what we see here. Since for any finite state machine, the name that we use for representing the states or the number of states is different, at any for any module which is implementing a finite state machine, we have to define a new type of variable. So the type def statement defines this state type as a 2-bit logic value with 3 possibilities, S0, S1, or S2. So let's just go through the different parts of this statement. We have type def, which is a keyword that tells System Verilog that we are defining a new type of variable. We have enum, which basically creates an enumerated encoding. So this is similar to the binary encoding that we have. The type is going to be a logic variable, and the size is 2 bits, bit 1 and bit 0. As for the states that we want to use, we use S0, S1 and S2, and that basically tells the system Verilog that assign S0 as 0, 0, S1 as 0, 1, and S2 as 1, 0. And then we name this new type as state type. So we can use whatever name we want. But now to be able to define the system, we need to have variables for the current state of the system and the next state of the system. That's what we do in the next line. We just create two instances of this state type. We just say state type with the size 2 bits. One is state, which is short for the current state of the system, and then one is the next state of the system. So if you remember from the design that we had, the next state of the system was something that was calculated using the next state logic unit, and then after it's been stored, it becomes the current state of the system. So that's what we basically do here. So as for the state register, you know how it's being defined. We use always FF and add sign here, and then inside we have the sensitivity list. So since we want to be able to reset our system asynchronously, inside the sensitivity list we have both the positive edge of the clock and positive edge of the reset signal. If reset is true, a state variable gets S0, so it becomes 0, 0. Otherwise, a state variable gets the next state of the system. But what is this next state? This is something that we define in the next state logic unit. So inside the next state logic unit, we have always comp, and then we have case, which checks the current state of the system. Since there is no input in the system, basically there is no condition for the arcs that we have for the transitions between systems. What we basically need to do is that we need to check the current state of the system, and based on that we can find the next state of the system. So we know that if we are at the state 0, our next state is going to be a state 1. If we are at the state 1, our next state is going to be at the state 2. If we are at the state 2, our next state is going to be a state 0. And as always, we have this default case 2 that we say if none of these things happen, for some reason, if we have a glitch or something like that, which the default case might happen, the next state would be S0. And finally, as for the output, anytime our current state equals state 0, Q becomes 1 or true. You can implement this using other ways too. For example, you can use always come to do the implementation here, and for that you can just say if a state equals S0, Q is 1, otherwise Q is 0, right? But this is another way of implementation too. So here what happens is that we just check whether a state equals S0. So you see we have two equal sign. So this is basically for checking whether two variables are the same. Don't confuse this with assignment, right? So when these two states are the same, the value of this parenthesis is going to be true, and that value is going to be assigned to the output queue. So to summarize, implementing finite state machines is very straightforward, since we have three blocks: the next state logic unit, the register, and the output logic unit. We basically divide our module into three different parts. One important thing to consider is that since the number of states might be different between finite state machines, you need to specify a new type that basically lists all the possible states and then assigns the proper encoding. And then after that, you create the current state of the system and the next state of the system using this new type that you have defined. And then the rest is going to be straightforward. For the register part, you will be using always FF. For the next state logic unit, you can use always COM. And for the output logic unit, you can either use always COM or just simply use the assign statement. It depends on the simplicity or complexity of your finite state machine.